Today's topic is a journal framework for designing evolutionary experiments to select a specific phage phenotype using neural network and symbolic regression. I am Hassan. I am in final year of my PhD in Diana Fusco Group at the University of Cambridge. So what's the motivation of my research? Usually experiments know the microbial environment, and that microbial environment select a phage phenotype for us. However, in this research, we want to do the reverse. That means we want to design a microbial environment in such a way that it select a specific phage phenotype for us. So how to do this? So to do this, I have divided the protocol into 4 steps. In the first step, I will get the phage time series data. It can be either experimental or synthetic. So for example, here the unknown environment is selecting the red phage phenotype. Then I can feed it this data into the physics-informed neural network, and that will discover the unknown bacterial time series for me. Once I have all of the time series, I can use the symbolic regression tool to get the governing equations, and then I can analyze different terms in these governing equations to know the underlying microbial environment. So to build the full protocol, I first benchmark the protocol by using the ground truth and see if the protocol is able to recover the ground truth or not. So to get the ground truth, I use the synthetic data by using the HM-based simulation, which is developed one of my colleague members, Aaron Smith. So the model is like there are 2 phages that can infect the healthy cells, then they replicate inside the cells. Finally, the cell dies, and phages are also subjected to decay, and the remaining phages go forward and infect new bacterial cells. So based on this model, I have obtained these stochastic time series data of the bacterial cells and the phages. So since I know the model, I can write the governing equations as well. These are the governing equations and these are the coefficients. And if I solve these governing coefficients, you can see that their solution is agreeing very well with the stochastic data. So in this protocol, I want to recover this ground truth. So the first step is to apply the neural network, and it is important to note that neural network will only see the phage time series. It will not see the bacterial time series. So I have given these 2 stochastic time series of the phages to the physics-informed neural network, and it has discovered the hidden time series of bacterial cells. And as you can see there, the discovered time series is agreeing very well with the 2 stochastic time series. So once I have all of the time series, I can apply the symbolic regression to get the governing equations. So the symbolic regressions have given me these governing equations, and these are the coefficients. And true coefficients is denoted by the cross marker. So you can see that the true coefficient and discovered coefficients are agreeing very well. There are some coefficients that have a very high standard deviation. These are corresponding to these equations or these terms, and this is happening because these terms are contributing only negligibly to the dynamics of the system. So in short, through this research, I am able to identify the microbial environment that is selecting the desired phage phenotype, and I have benchmarked the protocol using the synthetic data and recovered the true ground truth. So these are my group members, and thanks to all of them for providing their useful feedback throughout the research. Thanks.